Hey guys, welcome back. We've officially finished our first unit. We'll be taking the test on it over univariate data. We'll be taking that on Wednesday. So that is your deadline to have all of your homework turned in. Now last Friday I assigned the practice test, and I know it's pretty long. The actual test itself will be a little bit shorter, so sorry about that. But I'm going to go through the solutions for the practice test now. So if you guys had, as long as you've taken the practice test, you can go ahead and watch this video. That's what we'll be doing on Monday. And then on Tuesday, I'll be giving you guys a review assignment, just another review assignment. If you have any questions on the practice test, make sure you ask them. We are live with our office hours on Google Meets from 1 o'clock to 2 o'clock, so join us and get your questions answered before the test on Wednesday. Another good news is that the test score will replace your quiz score. So if you didn't do as well as you wanted to on the quiz, but you got to figure it out by now when we add the z-scores to it, of course, then your grade will go up whenever we take the test if you have a higher score from the test than you did on the quiz. So let's look at a few problems. These are the most missed problems I saw on the multiple choice section. So let's go over the difference between the wordings of these two questions. So it says, in a normal model, what percent of data are greater than 1 standard deviation above the mean? So if we are 1 standard deviation above the mean and we want to know what's larger than 1 standard deviation above the mean, we're referring to this area underneath the curve here. Okay. So more than 1 standard deviation above the mean. All right, cool. So to find the area under the curve, we go to second variable, so the distribution menu, and we're going to use the normal CDF, which is the cumulative density function. Our lower bound is going to be positive 1. Our upper bound is going to do 999. And we are centering at 0 with standard deviation of 1 because we're using the standard normal distribution here because we're talking about z-scores. Okay, so that's going to be about 15.86% or 87 or 15.9 if you just want to round up percent. All right, in normal model, what percent of data are greater than 1 standard deviation from the mean? Okay, so this is not above the mean anymore. Now it's 1 standard deviation from the mean. So how does that change our distribution, or how does that change our answer? So instead of just being above the mean, we want to know if it's more than 1 standard deviation away from the mean, which also would add the negative tail here as well. So this would be how many standard deviations we are below the mean. These all should be negative as well. I'm sorry, I just noticed that. Anyway, so you get the idea. Those are all negative z-scores because they are standard deviations below the mean. So our answer would now actually be doubled our last one. So we found the one tail going just strictly above the mean, but away from the mean would be 2 sides. Most of you guys, whenever you found the answers, you did one of them instead of the other one. So all right, let's look at another one. What z-score has 97.5% of the observations above it? So if the observations are above it, that would be this area here, and it's going to about 97.5% or whatever. So we want to know what z-score has 97.5% of it above it. So I'm going to go back here. Now that I have started out with the area, I'm going to use the inverse normal model. The area we're referring to is 0.975. Okay, standard normal because we're doing z-scores, and we're measuring our area from the right because we want to know how much is above it, and hit paste, which will give us a z-score of about negative 1.96. What z-score is the 97.5th percentile. So this is different because we're not saying how much is above it, we want to know the percentile. So that's measured from the left, and that's going to be about right over there. In fact, it's going to be a little bit less because we said it was 1.96. All right, so now we're going to do second distribution, inverse normal, which is the third option. We're going to do the same area, but now we're measuring it from the left. So if you'll notice, it's just going to be a positive version of the last one. So no big deal. So be careful. If they're asking the difference between something that's strictly above or below the mean, that's going to be only one-sided. If it's how many standard deviations from the mean would include both sides, negative or positive. And if it has a percent that's above the observation, that's going to be measured from the right. And if it's a percentile, those are always measured from the left. All right, school administrators, so those are the most common mistakes, so I just want to go through that real quick. School administrators collect data on students attending the school. Which of the following is quantitative? So quantitative has units and is not broken down into categories. So this is definitely categorical. Grade point average, that would be quantitative. The reason that would be quantitative is because our units are GPA, and it's going to be a continuous from all the way from 0 all the way up to 4 or 5. Whether or not they're an AP class, it's yes or no, that's categorical. whether they've taken the ACT, that's also categorical, yes or no. Which of the following variables would most likely follow a normal model? So normal model has to be unimodal and symmetric, so it can't be skewed to the left, can't be skewed to the right, but we're looking for the symmetry, something like this. Okay, so that's what we're looking for, and we just have to imagine what we would expect from these. So family income, that's probably going to be skewed to the right because you're going to have people who make much more than, and most of the variation is going to be on the high end instead of the low end. Is another way of saying that. Heights of singers in the co-ed choir, remember we said that would be bimodal because it's co-ed, keyword here, so that would not be a normal distribution, it would be bimodal. Weights of adult male elephants. All right, if they're adult male elephants, then it would probably follow a normal distribution. Okay, you're going to have whatever the average is. Okay, and then you're going to have some that are higher than that. You're going to have some that are lower than that as well. Okay, so as long as we're only referring to adult, if it was all male elephants, then it would be clearly skewed to the left because you'd have all the adolescent ones and the baby elephants skewing the distribution to the left. But if we're restricting it only to adult and only to male, otherwise, again, unlike co-ed, it would be bimodal. Scores on an easy test. If it's an easy test, it would be skewed to the left as well because most people are scoring really well. If it was a very hard test, it would be skewed to the left where most people are scoring low, and it would be skewed to the right by people who scored well on a hard test. So anyway, the correct answer would be C as in Charlie for the reasons discussed. Professor has kept the records of grades here in the class and wants to examine the percentage of students earning the different grades. So he wants to see the percentage breakdown. When we're dealing with percentages, I'm really struggling with this. Anyway, when we're dealing with percentages, there we go. We break down percentages with a pie chart, basically. Also, this is categorical data, so we're talking about A's, B's, C's, D's, and F's. Box plots are used with histograms and with quantitative data. Time plot is if we're seeing how something changes over time, so that's not what we're dealing with here. And a dot plot is essentially the same thing as a stem and leaf plot, which is also done with quantitative data. So the only one here that we actually use for categorical data would be pie charts and bar charts, but pie charts weren't listed, so bar charts weren't listed, so our answer would be a pie chart. Which is true about the data shown in the histogram? All right, so clearly it's symmetrical. Like this is perfectly symmetrical. Data never looks like this, by the way. Unless it's like a theoretical model of dice or something that actually looks about right. Anyway, distribution is approximately symmetric. That's true. The mean and median are approximately equal. Yes. So comparing the mean and median is one way to determine if something is skewed. And in this case, it's clearly not skewed to the right or to the left because, as we said, it was symmetric. So the mean and the middle 50%, the median and the mean are going to be exactly the same. So both of those are true. The median and IQR are summarized better than mean. Okay, so we can actually use the mean and standard deviation because this would be appropriate to use a bell curve with because it is actually symmetrical and unimodal. All right, so all of these are true except for the last one because mean and standard deviation are better than using median and IQR. So it would be 1 and 2, which is C as in Charlie. Two sections of a class look at the same quiz. Section A had 15 students who had a mean of 80, and Section B had 20 students who had a mean of 90. All right, so we have Section A, which had an average of an 80, and then Section B, which had an average of 90. So if I added these together and then divide it by 2, clearly that's going to be 85, right? So this would be a simple mean, but the problem is one of the sections had 20 students, the other one had 15 students. So we can't just calculate the simple mean, it has to be a weighted mean. So what we're going to end up doing is we're going to multiply the 18. Actually, let me just redo this real quick. All right, so to do a weighted mean, in fact, I'll just put it in the calculator to show you how I do it in the calculator. All right, so I'm going to go alpha x, that way I can show this. So the first one, we had an average of 80, and there were 15 students. So I'm going to do 80 times the number of students that did that, which was 15. And then I'm going to add the score for the second group, which was 90 times the number of students for that, which was 20. And then we divide by the total number of students altogether, which is 35. So what's happening here is we're taking between 80 and 90, and we're weighting it so that the 80 is multiplied by 15 and the 90 is multiplied by 20. And when we do this, we should get a number that's closer to 90 than 85, and that is correct. And the reason for that is because there were more students that scored an average of 90 in this group than the smaller group that only had the average of 80. So that means our weighted mean would actually be higher than that. All right, I think I showed a problem like that on one of the homework assignments. All right, your stats teacher tells you scored in the third quartile for the class. So the third quartile would mean you're scoring in the top 75%, so somewhere around here, meaning you scored only 25% scored above you or better. If we're looking at percentile, that means you scored higher than 75% of your classmates. So your Z-score is going to be between 1 and 2 somewhere. All right, so does that mean that you got a 75 on the test? No, because that would depend, it just depends on what the mean and standard deviation is. So what it really means is that you scored higher than 75% of your classmates. Can't really tell without the mean and standard deviation? Nope, because we know what percentiles mean. Can't really tell what this means unless the class distribution is nearly normal. It actually doesn't have to be. I just showed a normal curve because it's easy to show the area under the curve. But regardless of if it's skewed and we can't use the mean and standard deviation, we can still know what your percentiles are. So that's not true either. In fact, none of these are true. All right, the advantage of making a stem and leaf plot instead of a dot plot is that a stem and leaf display what? All right, so here we have histograms of states visited, which shows us the distribution, the shape, which is nice when we have a large set of data because we don't want to see the actual data points when we have samples larger than 45. The stem and leaf plot, or display shows the exact same overall shape, right? But the difference is it shows the actual data because we have our stems and our leaves, so you can see how it breaks down in each one of the groups or the bins. Okay. Now a dot plot is exactly the same as a stem and leaf, except instead of showing the actual data, it just shows dots, or an asterisk or an X or whatever it ends up using. Sometimes they use little pictures of something. Like if you were in kindergarten, you might do like little smiley faces or caterpillars or whatever you were graphing out, which kind of gives you the context, which is kind of fun. But anyway, so what's the difference between the dot plot and the stem and leaf plot? Well, the difference is that the improvement of the stem and leaf plot over the dot plot is that the stem and leaf display will actually show you the actual data itself. So satisfies the area principle, both of them do that, so no big deal. Stem and leaf display is for quantitative, dot plot. No, actually both of them are for quantitative data, so that's not true. Preserves the individual data values, that's it. Because whenever we use a dot plot, we don't get the actual data values, we can't actually see those. Shows the shape of the distribution better than a dot plot. It actually shows the exact same shape. All three of these would show the same shape. Sorry, that's wrong. So the benefit is actually going to be because it preserves the actual data points instead of a dot plot just showing the dots. 5-number summary of credit hours for 24 students in the stat class is given there. Which statement is true? So we want to know if there's any outliers. So to do that, we have to calculate the right and left fence. So the IQR is going to be 3. 18 minus 15 is 3. Times 1.5 is going to be 4.5. Subtract that from 15, which is your first quartile, which will give you a left fence of 10.5. Add it to your third quartile, which is 18, which will give you 22.5. So do we have any outliers? Well, this is our left fence, which is the fence for what would be an outlier on the minimum side, and the minimum is higher than that, so we're fine. And on the right fence, it is the maximum is lower than that. So because our max and min are within the fences, we don't have any outliers, so there are no outliers. Which of the following summaries are changed by adding a constant? So this is an example of shifting. So let me go over the difference between shifting and scaling. Hopefully this will be good. So I pulled this slide from a slide we're going to do in our probability unit. So on this one I was referring to rolling dice. So let's say we roll a dice, there are 6 possible outcomes, and it could be a 1, 2, 3, 4, 5, or 6. So that's these black dots here, and each one of those has the same probability of 1 6. So that's what I'm showing. Don't worry about it too much. So in the original data, if we could roll a 1 to a 6, what is the average? So the average between 1, 2, 3, 4, 5, and 6 would actually be 3.5. The total variation, I'm not going to go into how we calculate that, but again, it's just taking the deviations and then squaring them, then dividing by the number of the sample size minus 1. So anyway, that's going to be 2.9. Then we take the square root of the variation, which would give us a standard deviation of 1.7. Okay, so that's our original data that hasn't been messed with. But what happens if I shift the data? So instead, I'm going to take whatever you got for the dice, and I'm going to add 2 to it. So our lowest value of 1 plus 2 would now be 3. highest value of 6 plus 2 would now be 8. So we're just adding 2 to whatever the outcome we got. So what happened to our mean? Well, now our mean shifted over to the right with our data, and now it's going to be 3.5 plus 2, which would be 5.5. The variation, if you notice the spread of this data, it's the exact same data, it's just shifted over. So the measurements of spread, like variation and standard deviation, are going to remain unchanged because the deviation is calculated from the mean, and the mean shifted with the data, so it doesn't change the actual spread. But what happens when we scale? So when we scale, we're multiplying by some scale factor. So if I take your dice from 1 to 6 and I double whatever you got, I double that score. So 1 turned into 2, 2 turned into 4, 3 turned into a 6, all the way up to the 6, which turned into a 12. So what happened to that data? Well, it used to be here. Now it's spread out twice as far. It's actually spread out twice as far and shifted to the right, but just strictly doubled is what it's just doubling from this reference point or vanishing point of 0. Okay, so from here, clearly, our mean now went from 3.5 to doubled, which is now 7. Our variation is actually going to be quadrupled. The reason for that, I'm not going to get into it too much, but it has something to do with squaring 2. So it's going to be 4 times as big, which would give us a variation of 11.6. Then when I take the square root of that, like when you take the square root of 4, it's just 2. So it's actually going to be twice as big as well. So what you need to know is that when we scale things, the whole distribution changes because it's going to be scaled up by that scale factor, meaning it's going to be multiplied by our scale factor of 2. So our average is doubled and our spread is going to be doubled as well. Our variation and our standard deviation are going to, well, variation is quadrupled, but standard deviation is going to be doubled. So it is actually twice as much as 1.7, which is going to be 3.4, which is kind of cool. But when we're only shifting, we're taking all the data and we're just shifting it left and right. All of our individual data points are going to shift with it, like our mean, our median, interquartile, or not IQR. IQR, like standard deviation, is not going to change because it actually there's no deviation. There's no change in deviation because there's no change in the spread overall. Okay, so which of the following summaries are changed by adding a constant to each value? So the mean and standard deviation. The standard deviation is not going to change because there's no more spread added to it when we just shift values like we did with adding 2, but the median and the mean are going to change because they're going to be shifted with the actual data itself. All right, suppose the normal model describes the scores in history class. Parker has a standardized score of 2.5, so positive 2.5. What that means is that he scored 2.5 standard deviations above the mean. So if we're measuring his percentiles, it goes all the way up to the positive 2.5, which would mean that he scored whatever that percentile is using the normal CDF. So it's not that he scored 2.5 points above average, it's 2.5 standard deviations above average for the class. So that would be B. All right, in a normal model, what percent of observations are expected to be more than 1 standard deviation away from the mean? So it's not just a positive 1 standard deviation above the mean, it's also the negative standard deviation as well. So it's going in both directions. Again, these should be negative values. I really should have fixed that, but you get the idea. So it's not just greater than 1 standard deviation, it's more than standard deviation away from the mean. So it goes in both directions. Well, if we remember our empirical rule, the empirical rule tells us that there's going to be 68% of data that we expect to be within 1 standard deviation, so going from here to here. So how much is going to be on the other side? So that's going to be 32%. So a lot of you guys missed this problem and you said it was just 16 because you only calculated the tail from one side, but when we're talking about more than 1 standard deviation away from the mean, that's going to be a positive or a negative 1 standard deviation is the assumption. All right, number 12. In a normal model, what z-scores expect to have this many, that percent of observations above it. So if the observations are above it, it's not like we're measuring a percentile, we're actually measuring from the right. So to do that, we could just put it in our calculator. So second distribution, I'm going to do inverse normal, and we're going to measure from the right. So that's going to give us that value that actually looks familiar, which is closest to the -2. Okay, so if you're measuring the percentiles and you measured it from the left, having a little issues here. If you're measuring percentiles from the left, then you would get the positive value, which would be about +2. But because we're measuring it from the right, because we want to know the area of it above it, then it would be the -2. Okay, so again, a pretty common mistake we went over at the beginning. Suppose a normal model describes human body temperature. We're looking at ear thermometer. take track of the body temperatures of the next 82 patients at the doctor's office. What do we expect to be true? All right, so for measuring everyone's temperature, it should follow a normal model, but it's not going to be perfect. Also, if you think about it, you're going to have, the data is probably going to be skewed to the right, because you're going to people going to the doctor's office probably because they have a temperature, right? So it's not just healthy, normal people. We're talking about people that are sick. There also might be some potentially who have lower body temperatures from hypothermia instead of hyperthermia. But more than likely, people are going to be sick, and when they're sick, they're going to be hot. All right, so few or no patients will have a body temperature more than 3 standard deviations above the mean. Okay, so if we were doing 3 standard deviations above the mean, that area is very, very, very small. So I'm not saying it's not possible; it's just very unlikely. So I believe that is true. Okay, the histograms for those temperatures will be roughly symmetric. Yeah, we'll go with that. Roughly symmetric. It doesn't have to be exact, but that's good enough for me. You could argue that it could be skewed to the right. Exactly 68%. Okay, so this one's going to be false because it's not. This is only a model, right? We expect around 68% to be within 1, but the data never fits exactly the model. It was rare with the shark links that it was pretty well exact. So in this case, that one would be false. It's never exact, it's just a model. We would, if they said roughly 68% of the temperatures would be within standard deviations, 2 standard deviations from the mean. That actually should say 1, because 68% would be 1 standard deviation. 95% would be within 2 standard deviations, so that was wrong anyway, for multiple reasons. Okay, so the answer is C, as in Charlie. Suppose fuel economy. Oh, by the way, I do give partial credit. So this one clearly was the most obvious answer would be 1. So if you missed the second part here and you said it was 1 only, which I didn't even have that option, then I would have given you half credit. So there is oftentimes partial credit with those bimodal questions there. Suppose fuel economy rating measured in miles per gallon of the fleet of UPS truck follows a normal model. If it has a z-score of 1.7, that means it's 1.77 standard deviations above the mean, because this is a positive z-score. If it was a negative z-score, it would be 1.77 standard deviations below the mean. So higher than the average UPS truck. So that would be A as in alpha.